Question A asks us to write the expression for the equilibrium constant K of C for the reaction. So, I used the balanced chemical equation to do this. So, whenever you write the equilibrium constant, the products are on top and the reactants are on the bottom. So on the top it's H2 and I, and on the bottom it's HI squared. And the reason why HI is squared is because in the equation it's 2HI. So the exponent is based on the coefficient in the balanced equation. And question B asks us, what is HI at equilibrium? So I transferred the graph on the worksheet to the screen. And as you can see, the HI stops at 0.8. So the concentration of HI at equilibrium is 0.8 molarity. And question C asks us to determine the equilibrium concentrations of H2 and I2. And as we saw in the previous question, the molarity of HI at equilibrium was 0.8. So that means during the reaction, HI lost 0.20 molarity. The reactants always lose moles and the products always gain moles, so that means the reactants lose molarity and the products gain molarity. And H2 and I2 both gain 0.1 molarity because according to the conservation of mass, no mass is created or destroyed. So obviously the moles has to go to H2 and I2. And so it's split evenly because H2 and I2 both have 1 in the coefficients. And so you end up having 0.8 molarity of HI at equilibrium and 0.1 molarity for H2 and I2 at equilibrium. And question D asks us to make a sketch that shows how the concentration of H2 changes as a function of time. And as you can see, equilibrium begins right where the molarity stops changing. So I drew a line down to signify where that is. And as we calculated in the previous problem, H2 ended up with 0.1 molarity. Since that's 0.2, this has to be 0.1. So obviously it'll stop right here. Now as you can see on the top, it's not a straight line, so that's why I put a curve on the bottom, because the top wasn't straight either. Question E asks us to calculate the value of the following equilibrium constants at 700 Kelvin. So I'm going to use the equation that we used in question A. K of C equals H2 times I divided by HI squared. And using the values we calculated in question C, we can plug in some numbers. So at equilibrium, the molarity of H2 was 0.10, and the molarity of iodine was 0.10 also. And the molarity of HI was 0.8, and that is squared. And once you do all the calculations, K of C will equal 0.0156. And to calculate the Kp of the problem, we have to use the equation Kp equals Kc, parentheses RT, and parentheses delta N. So we can just plug in the numbers that we calculated previously. So Kc is equal to 0.0156, as we calculated right there. And the R value is 0.0821. And I believe I showed how I got that in a previous AP problem. And you times that by 700, because it gave us the temperature at 700 Kelvin. And delta N is the change in moles from products to reactants. But the only problem is that in the beginning, on the reactant side, you have 2 moles, and on the product side, you have 2 moles. So there was no change in the number of moles, so that will be 0. So we can just cross that out, and then it'll just be 0.0156, same as the K of C value. And question F gives us a different K of C value, and that value is 2.6 times 10 to the negative 2. And so we're going to use the K of C equation, except replace it with Q. And so if we just plug in the numbers, and the equation gives us 0.1 moles of H2 and 0.5 moles of I2. And if you do the math, it ends up being Q equals 8.89 times 10 to the negative 2. And as you can see, the Q value is larger than the K value. And if Q is greater than K, then the system is obviously not at equilibrium. And so the system will shift left to help get to equilibrium. And since it will shift left, that means it will shift in favor of HI. So that means the concentration of HI will be greater than the initial concentration.